video I will be discussing the Testbench code for an FSM or a finite state machine. I already created a project in ModelSim where I added my FSM entity and I compiled it successfully. The next step I'm going to do is to create a new script file by clicking on the new file icon, and then I will paste my Testbench code for the FSM. Ensure that you save the file as the same name as the entity. The entity name is FSM_Testbench. I'll be copying this and then saving the file as the same name with the extension .vhd. Once you have the correct file extension, you're going to notice that the code will be color coded, and you can also double check the extension right here. Next, I'm going to add the file that I just created to the project. Alternatively, instead of creating a new script file by clicking new file, you could have right-clicked here in the project tab and chose add to project new file. This way you will create the file and add it to the project in one step. Now that I created the file separately, I'm going to have to right-click here, choose add to project, add existing file, browse, and then navigate to the Testbench code, which is FSM Testbench. Click open, click OK, it will be added to the project. Now I'm going to compile this file by right-clicking on it and then choosing compile selected. Wait until it compiles successfully. When it does, you're going to see a green tick mark as usual. Next, we can go to the library tab and expand work, and then double click on the FSM Testbench to start the compilation or to start the simulation. Here we have all the objects or all the signals that we can look at. I'm going to select them all. So select the first signal, hold shift and then select the last signal, or Control A to select all signals, and then press Control W on the keyboard to add the signals to the waveform. Or you can also right click here and choose add waveform or add wave. Now we do not have to press force or clock, but rather we will just simply press F9 from the keyboard to run the simulation. So I'm going to press F9 multiple times to run 100 picoseconds at a time. I know it's 100 picoseconds because in my Testbench I assumed I defined the clock as a clock with 100 picosecond period. So every cycle will take 100 picoseconds. Now you can observe the output. This is the clock signal. This is the reset. So I started by making reset 1 and then changing it to 0 for the rest of the simulation. And these are the outputs. Before taking any screenshots, of course, we'll have to expand all necessary windows to ensure that the variable names show fully. This is the period we chose, and with the period set to 100 picosecond, we know that a complete clock cycle will require 100 picosecond, as you can see here. And we can monitor the output to see if it's the expected output, or if our code outputs text to the transcript window, we can expand it and then see if there's any output. Now I will go back to the code itself and explain it in more details. So I will double click on the Testbench to see what it looks like. We started by declaring the library files, and then we created an entity called FSM Testbench. As with other Testbench code, the entity for the Testbench does not have any ports, so there's no line here saying ports, because the Testbench does not have any input or output. It rather just has signals, and it assigns these signals values and then use them as inputs to the components we're trying to test. So the majority of the code is written in the architecture part. In the architecture part, I'm creating signals for the inputs and outputs. Here I have a signal called clock, a signal called reset, and these are initialized with a value equals 0. And then I have a signal called out signal for the output of the FSM machine which I'm trying to test, and in the FSM the output is 2-bit, it's a 2-bit vector. For our signal, out signal is also a 2-bit vector. We also initialized a constant named clock period, which is of type time, and set it to the value 100 picoseconds. This part or this value can be changed to say 100 nanoseconds or any other value that is of type time. Later in the code here, we're declaring the component to be tested. We're going to test the FSM machine or the FSM entity. So we're saying component, FSM, and component. And these lines of code are simply copied from our FSM entity. These are the ports of the FSM. We should copy them as they're originally written in the FSM.vhd file. Now that we initialize all the necessary signals and mentioned all the components needed, we can begin the architecture part officially. In the architecture, we're starting by instantiating the FSM component. We called the instance UUT, or unit under test, and this unit under test is an FSM. And then here we need to do the port mapping to map our signals of the test bench, which are these, to the ports of the FSM component. This is an alternative way to do the port mapping. So here, instead of sticking to the order of the FSM ports, which starts with the clock, reset, then the output, we used the name of the ports and then assigned the signal to the ports based on the name. So here we're saying basically that clock of the FSM, which is the signal, is equal to the signal clock, which is our signal here. It is more clear for the output. The FSM has an output port called output. Our test bench has a signal called out signal, and here we're saying that output of this FSM is going to be equal to out signal, which is the signal of our FSM test bench. In this case, since we used names for the port mapping part, we can shuffle the order. We do not have to stick to the same order. If we're not calling the ports by their names, then the order is necessary to follow. So this is still valid and acceptable. Next, we're gonna look into the next part of the code, which is right here, where we're beginning the assignment of values to our signals. Here I'm starting with the clock being assigned a value equals 0. Then I'm waiting for half the period, because when we say the period is 100 picosecond, this simply means that for 50 picoseconds, the clock is going to have a value of 0, and then in the second half of the period, which is the next 50 picoseconds, the clock will have a value of 1. So the clock will start with 0, and then it changes to 1, then 0 and changes to 1, and we can see that clearly when we run the simulation. You can notice, if I zoom in, you can notice that the clock in the first 50 picosecond is 0, and then in the next 50 picoseconds it's 1. So I zoomed in so it's clear. A full cycle will require 100 picoseconds to complete, as you can see here. Okay, now back to the code for the test bench. So after defining the process for the clock, where we simply create a loop. This process will repeat itself, and it will start with the clock being 0 for 50 picoseconds, and it changes to 1 for half of the period, and it will repeat. I have a separate process here that will run simultaneously with the first process for the clock. This second process statement will take care of assigning the values of the input signals. So in here we have a process that starts with the reset signal being assigned a value equals 1, and then this value is being held for a whole cycle, for a whole period, which is the 100 picosecond, and then reset signal is changed back to 0. In the final process, which will again run simultaneously, notice here we have 3 processes. They will all run at the same time. They will all be running simultaneously. The final process here will be taking care of the output and the assert statement. So here we're simply waiting for a whole cycle for 100 picoseconds, which is the amount of, the value stored in the clock period. And then we're using the assert statement to check if the output signal, or if the output is equal to 0, 0. If not, then we're going to report an error message saying that there's an error in state 0. Next, we're going to wait for another period, for another 100 picosecond, and then we will compare the output to the value 0, 1. If the output is not equal to 0, 1, then we will we will display an error message, and the cycle repeats. So this part will be doing the same thing, but for the next clock cycle, for the next period. Now, these messages are only being displayed if there's a mistake in the output. So if we go back to the output window here, or the transcript window, we will not see any reports, and this is because the output matches the expected result. So this condition was met for all states, therefore there was no error in the simulation.